idea. And in practice, you will write it like this. Span V1 through V, let's say is N. I hope that's right, N. And if V is not in H, then find E tilde that is in that shape, A1, V1, all the way up to AN, VN, minus V, that is this vector given outside this H. Then I explained that in the homework solution or the test solution, that is supposed to be U0, right? So that's, in practice, this seems like it's a really easy thing to code. And it means that computing this one by hand is very, very difficult. You're going to be using computer anyway. So this is a very easy way to code it, because this doesn't have to be orthogonal basis. Any basis in here, right? All you have to figure out is this coefficient such that this one is perpendicular to such that, what was the condition again? This is orthogonal to all the base member in here, k going through 1 through n. All the base member of H, which is just the n linear conditions solved using the row reduction, and you got that coefficients, and that is the projection. So it avoids computing, going through the Gram-Schmidt's process to computing it. But when we show this existence and one and only one thing, we use the Gram-Schmidt's. It's theoretically easier to use that. So this is practical way of computing the projection, which is A1, V1, all the way up to AN, BN. Okay? But theoretically, it's easier to write like this span. Write H as a span of E1 tilde up to En tilde. This is not orthonormal, but it's orthogonal, right? Orthogonal basis. Then what is the projection? Is the following, that each of them is just projecting this V projected onto E1, V projected onto En. Those are the coefficients. Right? So what do you get if you project the V onto EK tilde? It's just EK tilde, and all you have to figure out is the scalar, right? All the scalar is inner product of V scaled with that EK tilde. That's a scalar, right? If it is not orthonormal, then you have to divide it by the square of its own length. If it is orthonormal, that becomes 1. So theoretically, it's even easier to state. So why would you write orthogonal if it is a theoretical statement to just choose orthonormal without tilde? Then the formula is even simpler. You don't need this at all. So just simply that. It's k going from 1 through n. Then you have to prepare all that orthonormal basis. That's a bit of a work, and the coefficient gets ugly a lot. But it seems like this is better in practice. Okay? So let's think about this pH as a map from V to H, given by pH V going U0, right? And you have to describe what this U0 is, where, what is U0? How would you describe U0? Not by formula, but using the property, right? What is the property that describes U0? V minus U0 inner product with the U is going to be 0 for all U in H, right? That's going to be U0. And how do you know there is always one? How do you know there is a unique one? It is a part of defining this function, right? Given V, there must be one, and there must be one and only one. So that's the definition. Then I ask you to prove pH is what? Linear. Remember that? That was the homework problem. Let's see how it goes. All right, let's say, what are the two things that you're supposed to prove for the linear? V plus V prime must be PH V plus BH V prime. Is that right? That's what you have to show. So I think it's easier to prove this one. First, look at the right-hand side. We know the projection of V and projection of V prime exist, right? So let's say projection of V is going to be U0, and projection of this one, V prime, is going to be U0 prime, right? And we have a condition, what? V minus U0, U is 0, and V minus V prime minus U0 prime, U is always 0, where U varies from all over, right? So what do you want to do next? It's about the left-hand side, right? It's about V plus V prime, and you want to calculate the orthogonal projection of V plus V prime, right? Do you see a way to do that? By just having this kind of information in here? What is V plus V prime? Some vector. So you see that pulling out, how to pull out V plus V prime here from this condition? Add them both? Yeah. If you add them both here, keeping this same U, we have V minus U0 plus V prime minus U0 prime, U equals 0. You see that? Then how are you going to organize this one? V plus V prime, right? Minus U0 plus U0 prime. U inner product is 0. So there is this vector V plus V prime, right? And if you subtract U0 plus U0 prime, that vector is always perpendicular to whatever you choose from H, right? So what is the conclusion from here? Whenever you have that property, you know that projection of V plus V prime is U0 plus U0 prime. We found one vector in U such that it has this property. That is defining property of the orthogonal projection. So that is U0 plus U0 prime, right? But U0 was a PH V, and U0 prime was a PH V prime. Correct? That's why it's linear. So you have to, when you understand this, you have to clearly separate which condition, what you derive from which condition, and if you clearly separate it, and you will understand you actually understood the proof. So there's a scalar part there, right? But it goes just like the same. So scalar part. pH, AV must be A times PHV. I think that part's a lot easier. Okay? All right. Here's another thing about this map. Whenever you have a linear transformation like this, it's defined, we think about what is the kernel, what is the range of this one, right? Turns out range is easy. Let me write that again. pH going from V to H. What is the range of this map? Well, it's easy that it is sitting inside H, right? Because everything is inside H. The answer is actually they're equal. Then how are you going to show that? If I choose any element in here, there is an element in there so that it actually becomes equal. You see the quick argument? If I choose an element in here, W, what is the element that projects onto W? pH of what goes into the W if that came from any H, right? What was that? Answer? W. itself. Remember, if it's already on W, right? Think about projecting on the W. Correct? Yeah. So again, the W minus what is orthogonal to everything that is in UZ. That is orthogonal projection, right? Algebraically. What should be that? W. And then it's a 0. You couldn't do that if this guy's outside H, right? You can't subtract. This has to come from H. So also, not just intuitively, but also using this defining property, the W is going through there. So therefore, range is onto, right? Everything in there. So how about next thing that is attached to here? What is it? Null space of pH? Well, in this case, well, null space is the same. What is that? All the V's, right? The pH is a 0 vector. Is that right? Its projection is going to the 0. Let me give you a little picture here. This is H in R2, and here's a 0. Which do you think element in here, when you project it, landed on right here, 0? That's what this one is, right? When you orthogonally projected it, which one landed onto 0? Do you see that subspace? That's just this guy right there, right? So in this case, null space of orthogonal projection is that perpendicular line right up there, right? So, but this is not that case, it's a general. So what is the condition in here? That means if it is 0, that means a V minus, that is a U0, right? It's a projection. And 0 to all the U's that is in the 0. That you can rewrite that meaning of the projection like this. Correct? If it is a U0, no matter what V is, there's always going to be orthogonal projection, right? One and only one. So I'm just using it here. That is really U0 here. But that U0 is a 0, right? So we're looking at a V such that V minus this orthogonal projection is orthogonal to everything that is in H. Correct? Yeah. So this is a quite simple condition then. V, collection of all the vectors that is perpendicular to everything that is in H. It's a simple condition. So in this case, everything that is perpendicular that is in H is this line right here. So that's the condition. This one in here does not have any. Well, it's its name. Everything that is perpendicular to V is, they write it like this: span of everything that is perpendicular to. No, I think I was wrong. No one in here. This is everything that is perpendicular to the H, right? So they write it like this: H perp. That is the definition of this H perp. So this one in here is that H is a subspace, and this is a collection of all the vectors that is orthogonal to everything that is in H. So if that's H and that's your H perp, everything that is in here is perpendicular to everything that is in H. Okay? So here's a summary, and then I'll let you go. The range of pH is H itself, right? And the null space of pH is H perp. Collection of all the vectors that is orthogonal to every vector. All right, to quantify is tricky, so you have to look at this set. This is a perfect description. Collection of all the V. V has the following property: the V itself, the single element, is orthogonal to everything else in H. That collection is H perp. All right, this H perp and H is a very important element that arises in inner product space. So that's one thing that we're going to look at